The combination of resistance and reactance that describes the voltage and current relationships in real devices, materials, and circuits is collectively called the impedance, denoted by the capital letter Z and measured in ohms. However, resistance and reactance are and cannot be directly added together and must instead be calculated by using the rules for vector addition in the complex plane. So we'll start looking at that now. Recall from our earlier discussions that both capacitance and inductance cause a phase shift in the timing relationship between the voltage and current waveforms of precisely 90 degrees. We say that voltage leads the current in an inductor by 90 degrees, and that current leads the voltage in a capacitor by 90 degrees. We can easily remember this using the mnemonic Eli the Iceman, and we'll recall that this phase shift corresponds to 1/4 of a period, knowing that 90 degrees is 90 divided by 360 is 1/4 of one period, and hence this equates to a time shift of t over 4 or 1 over 4 times the frequency. So both of those tell you how much of a time shift in seconds there are between the voltage and the current waveforms. We can use the complex plane to see that rotating a purely real number by 90 degrees will result in that number either falling purely on the positive imaginary axis, or if we rotate it by 90 degrees, negative 90 degrees, we see that it falls on the purely negative imaginary axis. We can therefore represent a 90-degree phase shift as multiplication by J. So in this format, resistances are real numbers on the complex plane, as they do not cause phase shift at all. Reactances, however, are imaginary numbers on the complex plane, as both types, inductive reactance and capacitive reactance, cause phase shift. By convention, we say that inductive reactance causes a positive rotation of 90 degrees, or multiplication by J, and capacitive reactance causes a rotation of negative 90 degrees, which is a multiplication of minus J. Although we already accounted for that by saying that capacitive reactance is minus 1 over omega c. So there's kind of two formulations. Some people say capacitive reactance is 1 over omega c and it causes a minus J rotation. Other people say capacitive reactance is minus 1 over omega c and causes a J rotation. It results in the same thing. Capacitive reactance ends up being on the negative imaginary axis, and inductive reactance ends up being on the positive imaginary axis. We can therefore distinguish the rotational nature of inductive reactance from resistance by preceding it by the symbol J, again the imaginary unit quantity, the square root of 1. What this does is it corresponds to the oscillatory nature of the reactive component and also indicates that it can't be directly added to the resistance. Similarly, to distinguish capacitive reactance from resistance, it's preceded by the symbol minus J. If the complex plane is used with resistance along the real axis and the reactances are treated as imaginary numbers, then we refer to the resistance and reactance collectively as impedance. So here we show that if we look at the complex plane, we have resistors. They fall purely on the real axis. How big of a resistor? Well, that's the magnitude of the vector pointing in the positive real axis. There is nothing that points in the negative real axis. No component has negative resistance, right? If we look at the reactive components, the inductor and the capacitor, the inductor causes positive 90-degree phase shift. That means inductive reactances on the complex plane point straight up. They're given a magnitude J omega times the inductance. Alternatively, capacitive reactances point straight down in the complex plane. You see that its capacitive reactance is minus J over omega c. Technically, if we include the J, that's the impedance of the device. The total impedance of a resistor is R. There is no imaginary component. The total impedance of an inductor is J omega L. The total impedance of a capacitor is 1 over j omega c, which corresponds to minus j divided by omega c, right? Multiplication by minus j causes negative rotation. The resistance of a resistor is R, so the impedance and the resistance of a resistor are the same. There is no such thing as a resistor of an inductor or capacitor. There is no such thing as the reactance of a resistor, where inductors have reactance calculated by omega L, and capacitors have reactance calculated by 1 over omega C or negative 1 over omega C, depending on who you ask. Really what's important to remember is that the end result, capacitance need a negative sign in front of them, or the J needs to go in the denominator, and inductors have to have a positive sign in front of them with the J, I guess you would say, in the numerator here. So here what we see is that an inductor has a net impedance of J times angular frequency times its L, that would also be written as J 2 pi F L. So if you want to calculate the impedance of an inductor, that's the formula you will use, J2 pi FL. You'll take J, you'll multiply it by the reactance. So this gets used a whole lot in power systems. The impedance of an inductor is calculated by J times 2 pi times the system frequency times the inductance of the device. This is measured in ohms. Okay. A capacitor has an impedance of 1 over j omega c. That gets sometimes written as 1 over j 2 pi f c. All of that being in the denominator. It's also measured in ohms. Again, used a ton in power system analysis. So I would recommend committing, though that's a star if you can't tell. I would recommend committing those formulas to memory. The formula for inductive impedance, or for impedance of an inductor and impedance of a capacitor, going to be used very, very frequently in this class. Real electrical components can simultaneously contain resistance, inductive reactance, and capacitive reactance. Since inductive reactance and capacitive reactance cancel, real electric components will exhibit behavior that either looks like resistance plus inductive reactance, or they'll look like resistance plus capacitive reactance. Mathematically speaking, what we say is that the impedance Z is the vector sum of R and X in the complex plane. Therefore, that's why we use a boldface Z to indicate it as a vector Z. We could draw a little hat over it, a little arrow over it to indicate. We got to indicate somehow that this Z is a vector. In type, it's usually a bold. If you're writing by hand, a lot of times you put a squiggly line over it or something like that. So here we're showing two situations for complex impedances. In the first, a real resistance shown on the x-axis is vector added to an inductive reactance. Remember, inductors point up the imaginary axis by JXL. So we would say that the total complex impedance here, Z, is just equal to R plus JXL, right? That would also be written as R plus J omega L, saying the same thing right there. And this is going to result in a complex impedance that points in the first quadrant of the complex plane. In this second example here, we have the combination of a resistance, again lying in, I guess we could add the complex plane here, right? We've got a resistance that lies purely on the real axis, pointing in the positive direction. We've got a capacitance, and we know that capacitance lie on the negative imaginary axis. So if we want to add these, we would say Z as a vector is equal to R minus JXC. Another way to write that is Z is equal to R minus J divided by 2 pi FC, right? Where here, instead of using angular frequency, I used ordinary frequency, right? So very common formalisms. So let's do a few calculations of reactance and impedance, and we're going to start with inductors. We say the current in a 20 millihenry inductor is given by this function 10 cosine 10,000 t plus 30 degrees milliamps. Can we go ahead and calculate the inductive reactance and the impedance of the inductor? So remember, the key to doing this is remembering that reactance and impedance of devices are frequency dependent. So we were given the current, or sorry, we were given the voltage through the device. I believe we were given voltage through the device. Let me check again. No, we were given current. Okay, so it's I of t equals I max cosine of omega t plus phi. So what's important if we're determining impedance is we got to figure out what the angular frequency is. Well, from our problem statement, omega was the term that multiplies by the t equals 10,000 radians per second. Right. And if you have trouble remembering the units, remember it's got to be radians, it's got to be an angle. So x sub L is therefore equal to omega times L, that's 10,000 radians per second. We then multiply that by L, it was 20 millihenries. That's 20 e to the minus 3 henries. And so we get an inductive reactance of 200 ohms. So 200 ohms inductive reactance. If we want to call that impedance, well, we have to indicate that it's inductive reactance, so we just slap a J in front of it. It's equals J omega L. Technically, there should be a bar over this because this is a complex number, even though for a pure inductor it only has an imaginary portion. So we get J XL equals J 200. Still measured in ohms. Okay. So now let's do the same thing for capacitance. We've got the voltage across the terminals of a 5 microfarad capacitor is given by the voltage function 30 cosine of 4,000 t plus 20 degrees. We want to calculate the capacitive reactance and impedance of the capacitor. So again, the reactance of the impedance of the capacitors are frequency dependent. We had V of t equals V max cosine omega t plus phi. So we just compare it to what we were given for that formula. We don't care about V max. We don't care about the phase shift when we're calculating reactance value. Omega equals, in this case it was 40,000 radians. Right. So the formula for capacitive reactance is a little bit different. X sub C equals 1 over omega C. Right. So that's equal to 1 over 40,000. We multiply that 40,000 radians per second by 5 microfarads. Micro is 10 to the minus 6. We get 50 ohms. So we would say that this has 50 ohms of capacitive reactance. If we want to turn that into an impedance, we just say Z sub C is equal to minus J X sub C. And that gives us an impedance of minus J 50 ohms. I personally prefer this notation of using the negative sign to indicate impedance as opposed to reactance, because negative 50 ohms makes no sense. There is no such thing as negative 50 ohms. Negative J 50 ohms just means a 90 degrees phase shift in the negative quadrant. So I kind of prefer that notation there. You're free to use whatever you prefer. So we're going to end with a resistive calculation. We've got the voltage across the terminals of a 100 ohm resistor is 25 cosine of 25,000 times T plus 20 degrees. calculate the resistance and the impedance of the resistor. If this was on a test, this would be give me. Resistance and impedance of a resistor are not frequency dependent. They're only dependent on the material properties. The resistance of the resistor does not change. It's 100 ohms. The impedance of the resistor is 100 ohms. No calculations necessary. You can go straight to it. So